Okay, hello, hello. All right, all right. So let's get this started. What you just saw there is collaboration, solving hard technology problems. And there's only one thing harder than making a laptop present. There's only one thing harder, which is making multi-brain servers, right? So I'm Andres, I work at Google. You'll see me on the security track. You'll see me right now. Also tomorrow at Future Technology Symposiums. Who's this guy? This guy is a Tintenfisch, which is German for octopus. He has 8 tentacles, 3 hearts, 9 brains. I'm going to tell you why that matters in a second. Just keep that in mind, right? So you've seen this. Zane says Moore's law isn't over. Other people say it's over. Let's not have that debate right now. Some things are happening, though. This is tapering off. You can see the curve tapering off, right? Things are not scaling up anymore. It's not exponential every year. So here's Moore, and he's saying, hey, goodbye, I'm leaving the building, no more, law is over. And here's you, and you build systems, and you're trying to get compute throughput, and you're trying to keep up with your business. And you're saying, okay, what do I do? I guess I'm going to add a ton of GPUs, and IPUs, and DPUs. And they're saying, yeah, sure. Just instead of having one CPU and a single monolithic server, now your server is a bunch of things, right? It's a big network with BMCs, and TPUs, and IPUs, and everything else. So how complicated is my system going to get? Your system is going to get incredibly complicated, right? And that's where it goes back to the Tintenfisch. Your system is going to have many tentacles, many brains, many hearts. It's going to be a pretty complicated thing. Now, none of this is news to you. You've been hearing this since the beginning of OCP, since last year. You know, thousands of accelerators, bisectional bandwidth, big trays with loads of stuff. What OCP does fantastically well is you're going to get the hardware specifications, right? People are going to go out there. They're going to have racks. They're going to have trays. They're going to have power adapters. They're going to have PCBs. The PCBs are going to have blinking lights. There's going to be DIMMs and dissipators, and there's going to be copper everywhere and cables. And these arrows are telling you, oh, yeah, I'm just going to plug it, right? So that doesn't work, right? All the hardware is amazing. None of the software works. Right? You might thinking that we're being hyperbolic, but the reality is you have to do a ton of things in the data center in order to deploy 1 million samples of anything, right? It's not just a demo. We all know that, right? But you have all the system management CUJs, critical user journeys, all these workflows. They all need to work. They need to work reliably. They need to work all the time. They need to work scalably. You cannot involve humans, ever, right? So just actually booting a system this complicated, it's a journey in itself. It is a complication. Turning up a system, you know, taking ownership, rotating the certificates, changing the keys, wiping the storage, reinitializing the storage. What else is in here? Installing the software, upgrading the software, dealing with all your CPUs, right? The NICs have CPUs now. If you have a system with a bunch of 200 gigabit per second NICs or 400 gigabit per second NICs, and you have like 8 of them, and you're trying to achieve all this bisectional bandwidth, and you have all the BNCs, suddenly you have 12 CPUs in your system. All of them have Linux stacks. All of them need to be upgraded. All of them need to boot and talk to each other. You have roots of trusts. They all have cryptographic identities. I can keep going on. I can do this all day. I'm like Captain America. I can just keep going and going with all the problems that you're going to face, right? So we're trying to tackle this. We're trying to, you know, as a hyperscaler, deploying millions of these machines with all this complexity, we don't want our back to break. Our back is going to break if we don't do anything about it, right? So we're trying to tackle this, and we have a few organizing principles, and we're trying to involve you into this software journey. Because we know the hardware is amazing, and the hardware is going to eat all the power that we can give it to. So the first one is modeling, right? We'll talk more about it later, but the way we're going about this is from a first principle and from a structured way. We have an entity relationship-based model of hardware. We'll show it in a moment. But the point is that you have templates that tell you what the machine SKUs are like, and as-built models that tell you each specific instance and all its various identifiers. What do you need a model for? The first part is that we divide the machine into pieces, into individually manageable pieces that then you can compose together to build new SKUs. So imagine the basic board, the one that Zane showed today. That would be one piece. We call it an arena because it's a self-contained hardware element. But Here comes a tray of GPUs. That's another arena. Here comes SmartNICs, another arena. Here comes a storage tray, another arena. You want to do different SKUs, composing these things together. You're just composing arenas. So that is the main insight here. Another key part of this, everything that an arena do has to support out-of-band management because we are a cloud provider. And we sell the machines to other people. And other people don't want to know anything about MCE logs or fan RPMs or telemetry sensors or thermals. So all of that has to go on one side while the user enjoys things on the other side. And the last part, of course, is you put it all together, and suddenly you have these individual hardware arenas that are no longer a machine, but they can make up a machine. And then making a machine out of shared arenas becomes a natural and organic extension of the paradigm, right? So let's break this down a little bit. For modeling, we're proposing for you, if you're interested, to come and let's make it a future OCP contribution. Divide is natural to OCP modular hardware systems. This is what people have been driving, have been talking about today, have been talking about for the last year. People keep just bringing this up. Out-of-band management is something our hardware management team is very interested in it, and that we hope to make a lot of progress in the OCP hardware management part. And for disaggregation, we believe it's a standardization opportunity if we come around this paradigm. So this is an actual entity relationship model. It's not meant for you to understand it. It's meant for you to be scared of it and come work with us on the idea. The main point is that it makes sense to automation. If you're trying to upgrade the software of a machine, now you walk this DAG, and you know what to do at each step, and you don't have to rewrite it for every single new machine that you're developing, right? You apply the pattern, the iterator pattern over and over again. If you need to power cycle, you think power cycle is like something natural, right? It's germane, just press the power button. You don't just press the power button when you have GPU trays and SmartNICs and storage trays. It doesn't work like that. Things need an order of operations, right? You're thinking about rotation, all those things. Again, you need this. You need some way to teach your systems how to do it for each new SKU. So that's our proposal here. I already talked about arenas and out-of-band management. We believe arenas, it's what it says there. I already explained. They're self-contained hardware islands that you can build and compose into many new things. Critically, they have to have out-of-band management because that's what enables the composition. If you're talking to an out-of-band BMC controller, nothing changes as you add more and more arenas to your system. The only thing that changes is that you need to walk more arenas, but you already have the basic building blocks in place. This is the part where our data center flows that really don't necessarily make too much sense in an OCP context because they're very unique to handling data centers all over the world, et cetera, et cetera. They are able to adapt to each new system SKU by walking the model. As long as systems are expressed as a model and are built as arenas and the software can talk out of band, we can do this over and over again. We can be Captain America and do it all day, right? And that's why we're trying to do this. We're trying to tame this complexity that composition is bringing to us through these principles. So call to action. Compute is complicated. Compute is no longer a single CPU. Compute is a network of different compute elements. Opportunities to come together and tame the complexity. Come talk to us. Let's talk about modeling. Let's talk about arenas. Let's talk about composition. Let's talk about out-of-band management. Questions, interests, you can contact me. You can contact most of the Google people here in attendance. We have our BMC team here. We have our hardware architecture team here. We have firmware team here. You can talk to any Googler, not just Andres. I'm way ahead of time, but I'm done. So thank you for your attention today. Thanks.